Hi, my name's Clay, Senior Manager of Data Science here at Localytics. We are a app marketing and analytics platform working with some of the world's top brands in multiple verticals, really fun stuff. So, so what's something that's common to all mobile apps? Well, users download them and users leave. There's a mobile retention crisis, as many have been calling it, where 90% of mobile users don't come back after 30 days. Um, People have seen that the famous aha moment from Facebook that if you make 7 or more friends in the first 10 days, your churn rate drops dramatically, um, and so on. But people want to understand why users churn so that they can do something about it. And then also who's going to churn, predict who's going to churn so that you can intervene in some way. So we have Localytics predictions, just a little thing about me. Scala engineer, greatly prefer Scala, former Python, also great, and a petty dabbler in data science. So how does this work? Well, I'll give you a quick demo of the product. This is not a sales pitch, so this will be brief. Here we have a prediction for a demo app where you define churn as someone not viewing a product in 14 days. You can define churn in many different ways. Sometimes it's app open, sometimes it's purchase. If you're an e-commerce app, obviously you want to look at people who are in your purchase funnel. So we divide people into high, medium, and low. You could create an audience of people who are high churn risk users so that you can intervene in some way, push message, email, remarketing, custom, like your own thing. You could call them up if you want to. We allow you to do that. Most importantly, we give the ability to ascertain why people are churning. So we have top related attributes. So if you're like, for example, gender, whether you're push enabled, your device, this gives you some intuition as to why people are churning. And then we look for your aha moments where, for example, in this app, if you've checked out 3 or more times in the first 7 days, you're 45% less likely to churn. So this gives you a lot of intuition as to why you're doing, or like why people are churning, what keeps them on board. And so it allows you to, for example, alter your app experience to encourage these behaviors and get people to stay. So how does this all work? Well, we go off of historical data. Obviously, as an analytics platform, we have access to a lot of data. Events with attributes, sessions, locations, funnels, flows, retention, LTV, even information from your retail locations that you put in. We churn through those logs, or we work through those logs, and we can detect churn, conversion, engagement, provide indicators so that we're not providing just a black box model. And you can use that towards optimizing your campaigns and ultimately improving your retention in your app. So you can do that with multiple touch points like push notifications, emails, Facebook marketing. These all have different costs, but it allows you to sort of determine what is your best strategy. We just provide the tools to enable you to do so. So how did we get here? Well, about a year ago, we started working on this project. We wanted to work in Spark because it was a new hotness and also something that I'm the most familiar with. And so we want to use MLlib. It's a good scalable platform. Who here has used Spark and MLlib? All right, so not many, but basically Spark is sort of touted as a new Hadoop, the new framework for aggregating large amounts of data and working with it in a good and easy manner. So with the aggregation that we did was we would create this full view time series of a user's lifetime. While that was super powerful, it required tons of compute, thousands of cores over like hours. I'm talking like 24 hours with 1,000 core cluster to create this like random forest model that was incredible, great results, like double-digit retention, reduction in churn, but this was not scalable. It absolutely crushed us. So we went back to the drawing board. So beta, we went back to the drawing board and we computed simpler aggregations because we realized at the end of the day, like the hard part of this is turning terabytes, petabytes of logs into a vector that you could feed into a machine learning model. Well, we went back to the drawing board and we redesigned all the aggregations to work as monoids. I'm going to get into this later, since it's a term that many of you might not have heard. But that provided a ton of benefits in terms of just like reducing the aggregations, where it's like 1,000-fold smaller reduction in memory footprint. However, model training still took too long. We had an SVM. Any of you have worked with support vector machines, logistic regressions, like there are a lot of levers to tune, a lot of hyperparameter search to get the right model. And we are creating a model for each customer because every single app is unique in not only the interactions, but also its implementation. Some developers have implemented the app with different events, different patterns of events, some like very sparse, some very heavy, some very like heavy in attributes. So we needed to create models that were flexible to work with all of these. So we also want to add interpretability. The problem with the random forest is that we would throw these models at customers and they wouldn't know like what this means. They want to know why users were churning. And because we were working across so many dimensions, we had to use the hashing trick, and that made the model a black box. So still not ideal. So we reach our current state. BGNBD, so beta geometric negative binomial distributions. Probably something, not a standard machine learning model. It's actually a model from statistics to the model for repeat transactions by a user. We have a current custom implementation that we're planning on open sourcing soon, very exciting. And then decision tree from MLlib we're splitting into high, medium, low. Excellent work by Mark, who is over there. This has monoids all the way down. Like the model itself is a monoid. All the aggregations are monoid, and it provides results just as good as a random forest and SVM with absolutely minimal compute. And it allows us to have the additional resources towards interpretability. So the model itself creates an output, and then we're able to scan through the inputs and determine what has created that result. So victory. And then currently in testing, we're very excited about this. We are implementing survival regressions, so accelerated failure time. It's very similar to a Cox regression where it gives a reason why people are dying. Like it's very common in epidemiological research where you see like, for example, different types of cancers, different types of genes that relate to like lethality or like time until death, which you don't want to think about your users dying, but in Churn, they're dead to you. It allows for great interpretation on like individual factors that relate to churn. Unfortunately, this relies on data frames. I don't know who has used data frames in Spark. They're awesome, they're fast, they're the future, but you lose type safety, which really hurts development time. And it's also very, very new in Spark 1.6.0, and I don't know if you've ever used like a 0.0 version of a Spark, but it's buggy and tends to just kind of die on you. So, and then future directions, we're working towards neural networks for more flexible predictions and better dimensionality reduction because we want to actually add more dimensions back into the model to gain a little bit better insights, and then moving towards a specialized data store for user vectors. So instead of relying on log aggregations, actually just storing a vector for a user so that we can pump it into multiple machine learning models. So what techniques do we use? Well, there's the BGNBD. No big deal because it relies on 3 very simple factors. Recency, so how recently have you seen a user? Frequency, how many times have you seen that user? How many times has that user performed a transaction? And T, total time. So with those, you gain a lot of insight that basically performs just as well as any other model, like all the factors in the world, gender, age, whatever, like this captures almost all the information. And so the intuition here is that if the user has performed a lot of actions, but suddenly you don't see them, like, well, chances are they are no longer alive to you. So like here, the red lines represent an action being taken, and the blue line represents the probability of them being alive. Well, if they've just performed an action, chances are it's very high. And if they perform consistently perform lots of actions, their probability of being alive increases. And the longer it's been since you've seen them, their probability of being alive like to you decreases. It's a very simple intuition, and it works out empirically that like if they perform a lot of actions and you've seen them very recently, chances are they're still a user, right? Like that is a very simple, intuitive thing that most people will understand. And so if they perform lots of actions and you've seen them recently, chances are they'll perform lots of events in the future. This notion is captured by a Poisson distribution that creates a rate. So you're trying to predict the rate in which they're producing actions and basically a coin flip, a beta distribution to determine if they're still alive. So moving on to monoids. I've said this word a lot. If you go on Google and you ask, like, what's a monad is just a monoid in the category of endofunctors. That means probably nothing to anyone. What's a monoid? A monoid is a semigroup with an identity. So what does that mean? This is the only math slide. It just means that there's associativity and identity. A plus B plus C equals A plus B plus C. It's very simple, but an incredibly powerful concept because your data comes in the form of logs. Like how often have you used a data set that has come very nicely in the form of a clean vector that you could feed into a neural network? It never happens. Maybe if you're on Kaggle sometimes, but even then there's like cleaning that you have to do. So you're usually dealing with logs and you have to aggregate those logs by user and create features for those users. Well, turns out analytics is mostly just about counting things. You're taking averages, sums, counts, and creating metrics for that. Well, sometimes you need more, and like it's very easy to think about a count where you just count every single time an event occurs for a user and you can add those together. Well, integer addition is a monoid. Like 1 plus 0 equals 1, 1 plus 2 plus 3 is the same as 3 plus 3. Well, if you're able to convert a log into a monoid, then you're able to do some powerful aggregations. Well, we did that, and then we realized we're still hitting out of memory issues. So what did we do? Probabilistic data structures. These are awesome. These are super fun. In that you're able to obtain approximations of distinct values, frequency estimation, percentiles, membership, mean, standard deviation, variance, kurtosis, skew, at a fraction of the memory footprint. I'm talking on the order of, for 10 to the 7 elements in raw data, it's approximately 40 megabytes, 2 kilobytes, and for cardinality estimation with a log-log counter, which is huge. Like normally, if you want to get the number of distinct elements, you'd have to move them all into like some sort of hash set and keep track of all those elements, and that's going to be like at least 7 megabytes of memory. And we're dealing at greater than 10 to the 7, we're dealing at the level of petabyte scale logs. So you want to gain as much efficiency in your log aggregations as possible. And you're dealing with tunable error too. Like the 40 megabytes to 2 kilobyte ratio is 4% error. If that's not tolerable to you, you can tune it down to like 1%, 0.1%. And the idea that your logs are perfect, that they are just golden data is a fallacy. Like customer data, it's dirty. It's not going to be perfect. It's you have repeat events coming in, you have events that are lost. So there's an error that's built into your data. So the idea that you need perfect aggregations is sort of a notion that unless it's something absolutely mission critical, should not be the case. Like most machine learning models will work with approximations. So this is an example, this is a toy example of the way we have a record. So let's say a customer record has a customer ID, a session ID, an event name, and a session length in seconds. You want to aggregate this into this record aggregator that's the number of distinct sessions, their top events, and session stats. Well, you turn each log record into an aggregate record where it's you put the session ID into the hyperlog log, you put the top events into the count min sketch, and the session stats into a moments. And in Spark, you're just able to do a reduce by key. It adds them all together per user so that for every single user, you're just able to get like their mean session time or top events. And this requires a minimal memory footprint and will just save you tons of headache in the future. So what else does this allow? Well, it also allows you to chunk logs together, like months of records into one. So like we aggregate on the level of days, so that for every day we have a persistent monoid for all the actions that a user is taking on a day. Well, we're able to aggregate this across multiple months so that you have everything that the user's ever done in a nice clean record. But also we're able to split this so that we're able to blind ourselves to create training data. So that we have a time machine basically where we're able to look months back in the past and blind it to records in the future from a set point and use that as labeled training data. So how do we work with unstructured log data? Well, we have a project called the Tesseract. A Tesseract is essentially a four-dimensional cube, but in the Marvel universe, it is a device that enables you to transport yourself between time and space and dimensions. And we are transporting ourselves between multiple high-dimensional spaces. Essentially, we are able to turn dirty logs into which contain things like, nasty customer inputs. They're just typing things, or like there's typos, or there's input like bad test data because who knows, like they're just integrating the product. Unique identifiers. Some fields just might be phone numbers. They might be database row numbers. You have no idea because you want minimal data scientist impact, like looking at every single customer's data set to determine what's valuable. Currency, that's obviously a numeric attribute, but has usually a currency symbol in front of it. Numbers in the form of strings, different date formats, it's a nightmare. And we want to create a system that automatically works for as many different customers as possible with minimal impact. So, it doesn't seem that bad, right? Like you could try to parse dates, you could try just coercing values together. And that just tends to blow up on you. Like it creates tons of dimensions. Even if you just take like, for example, phone numbers, that's a 10 to the 9th space. Good? All right, excellent. So what the Tesseract does is it takes essentially a key value, string and string, and it tries all the different combinations of, is it categorical, is it numeric, is it a date feature? It bins numeric features if you need a model that only handles like one-hot encoded categories. It detects unique identifiers and throws them out because they're not at all useful to you and will just cause either like bad training values, like just terrible overfitting. And it's utility to convert between multiple vector types. So MLlib, Scala vectors, Algebird, ND4J. We're adding a few more, but those are mainly the ones you need. If you could get it to a Java array, you're pretty set. But in this process, we learned feature extraction is hard. It is probably the crux of a data scientist job to extract features from unstructured data. Even defining labels is hard in a non-contractual churn setting. Like, how do you define churn? We define it as inactivity for a period of time because we wanted a flexible definition for customers, but it might be completely different in your context. It could be failure to renew a contract. It could be lack of purchase or like lack of a certain number of purchases. But using monoids all the way down the chain helps this because it enables very easy aggregations. Interpretability, it turns out to be very important to customers. You can't throw black box models at them just saying with like grade F scores because they want to know. Like if you're providing a product, they want to know why it's producing an output. And of course, stability and efficiency. The fact that your jobs run consistently and doesn't wake you up at 2 a.m. to like, to cold sweats. I'm sorry, Mark. Is way more valuable than like 0.2 increase in your F1 score. It is much more important to create a stable system. So the advice that I have is that if it's going to take longer than an afternoon to write, or you plan on running it more than once, write in a strongly typed language with tests. Otherwise, it's just going to be held together by shoestrings, and it will just ruin your nights. So where are we going with this? Well, we plan on implementing a deep belief network for clustering, which is currently in flight right now. It's going to produce some cool stuff. as well as RNN-based prediction of sequences, so that we believe a sequence of actions will result in a churn, so that we can bring up those warnings more quickly to customers. Any questions? Yes.
So the probabilistic data structure, is that assuming a Gaussian distribution?
No. So the probabilistic data structures all have the principle of basically being built around different types of like approximate hashes. So none of these, well, a hyperlog might, no, none of these assume a Gaussian distribution. They're built mostly around like hashes. So like you provide multiple hash functions, it creates a table of them, and as you put in inputs, it will alter the hashes so that you get an approximation of the value that you want. So hyperlog logs can be used for distinct values without being aware of every item that's being fed into it. And that's extremely valuable because if you're dealing on the order of billions of items, you don't want to keep a running list of a billion unique items that you're counting over. Yes. Yes, so we're planning on open sourcing the Tesseract. It's built primarily for use with Spark, but we'll take any sort of list of map of string of strings and transform them into something where you could convert them into a vector you're choosing.
Okay.
Yeah.
Great. And the second question is, could you explain a little bit about the your last slide, the RNN-based sequence prediction?
Yes, sure. So recurrent neural networks are great at predicting sequences. Actually, there's nothing on that slide. So we would have a sequence of actions in a user session or multiple user sessions where you see that they have, for example, opened the app, shared a photo, liked a photo, experience like some action where like they got a photo like, and they continue doing that sequence. But what if you have an action where it's like add to cart, nothing, and then like you don't see them for 6 months, or like they disappear on you? Well, we can find that sequence of actions that usually results in them disappearing on you and alert you right away.
I see. And are you guys already building these, or is this
Yeah,
research?
so these are in flight. They're kind of in testing and validation because one of the requirements we have is that we're building models that work for multiple customers. And so like even if we see promising results with like a subset of customers, we want to be strategic about we're making things that just make things easy for people. And a lot of these are more powerful, sort of hard to use tools. And so we want to align it to our product vision of using machine learning to enable marketers to make like easy decisions.
Thank you.
Yes.
With something like a neural network, or even more so with an RNN, you mentioned the importance of the model being interpretable. That seems to be a challenge with something like a neural network or an RNN. So how do you sort of, I guess, straddle the two requirements when they seem to be almost, I guess, not overlapping in any way?
Yeah, so the way we usually handle that problem for non-interpretable models is that we rerun input data and we find like the combinations of input data that yield the results that we want, and we float those upward, because it's not true like just about like the coefficient on a particular vector or particular column on a linear regression. We want this to be like basically show that like this sequence usually ends in a churn, and so like trying to make that as easy as possible in a product is definitely difficult. And with a neural network, you tend to lose interpretability. So we're working on different strategies to get some interpretability out of them, and currently they're usually around refeeding training data and finding kind of key examples that exemplify the effect.